In introductory dynamics, we tend to treat massive industrial rotors like this one as simple kinetic energy storage devices, flywheels designed to keep a system moving smoothly. But when you take these multi-ton components and spin them at high velocities inside a moving vehicle, like a naval ship pitching in heavy seas, a completely different class of mechanical risk emerges. Any change to the vehicle's orientation forces the spinning rotor to move with it. This creates immense, highly non-intuitive cross-axis forces that push violently against the rotor's mounting bearings. This FEA model displays the equivalent elastic strain resulting from those forces. The high-strain color gradients at the outer edges map the intense structural consequences acting on the rotor material itself. Preventing catastrophic mechanical failure in aerospace and naval systems requires predicting these hidden stresses. That means engineers must master the mechanics of gyroscopic dynamics. Gyroscopic stability is a universal mechanical principle. It is the primary mechanism spacecraft rely on to maintain precise orientation in orbital environments completely devoid of friction or gravity. During World War II, it was the critical component in mid-century aviation, driving both aircraft autopilots and the complex tracking mechanics of anti-aircraft gun sights. To solve standard Type 1 kinematic problems for any of these systems, we have to precisely map two fundamental properties: gyroscopic rigidity and torque-induced precession. We start by stripping away the complex machinery and establishing a clean coordinate system for an isolated, rotating, rigid body. To map the angular momentum, we apply the right-hand rule. By curling the fingers of your right hand in the direction the disk is rotating, your thumb points straight outward down the axis. This defines the spin vector's exact direction. This gives us our first property, gyroscopic rigidity. Without an applied external force, this spin axis will remain absolutely fixed in a specific direction in space. Note that true rigidity is distinct from torque-free precession. Torque-free precession is just the natural, unforced wobble of a spinning body in space, where angular momentum stays constant but the velocity vector shifts. The actual gyroscopic mechanics we need to calculate only trigger when an external torque actively forces that locked spin vector to move. We can visualize this using a familiar physical model, a standard spinning top. Here, gravity acts as the external torque on the mass. Two opposing vertical forces act on the top. Weight pulls downward from the center, while the ground's normal reaction pushes up. Because they are offset, they create a rotational moment, an external torque trying to tip the mass over. But assuming rotational speed remains constant, the top does not simply fall over in the direction of the applied torque. Instead, the spin axis moves at right angles to the intuitive direction, tracing a geometric cone in space. This is torque-induced precession. Gyroscopic precession is the core physical mechanism that converts any applied cross-axis torque directly into perpendicular angular motion. Bringing this vector math back to the industrial scale reveals exactly what is at stake structurally for heavy machinery. We can assign our primary spin vector directly down the massive central rotational shaft of this turbine. Now, introduce a sudden external change in orientation. Imagine the host ship executing a sharp yaw or pitch maneuver in the water. This external vessel movement acts as a forced precession vector, an applied motion physically forcing the entire machine to pivot. Because the heavy rotor possesses gyroscopic rigidity, it violently resists being forced out of its original orientation. This massive opposing resistance generates the reactive gyroscopic couple, an equal and opposite cross-axis torque that strikes completely perpendicular to the original motion. If engineers fail to accurately calculate it, this reactive couple is the exact force that shears mounting bolts, shatters bearings, and destabilizes heavy vehicles. The mathematical laws governing this gyroscopic couple scale perfectly, regardless of the physical dimensions of the machine. The exact same vector logic used to secure a multi-ton engine is applied to fabricate microscopic silicon MEMS vibratory gyroscopes, which guide modern digital navigation. This FEA strain model of the industrial turbine shows the direct physical manifestation of that exact same math, mapping the extreme elastic strain resulting directly from the reactive couple. Every kinematic problem relies on calculating a strict operational triad: the direction of spin, the direction of precession, and the resulting gyroscopic couple. Whether you are designing microscopic silicon sensors or protecting a massive naval turbine from tearing itself apart, structural survival in a dynamic environment dictates that you must mathematically master the spin.